Hello, welcome to my talk on model categories and Whitehead's theorem. So I'll be talking about the basics of model categories, and I will show you some interesting applications, including an overview of the proof of Whitehead's theorem, and some interesting model structures, and how you can view, for example, homological algebra from a model category theoretic perspective. First of all, we're going to do some topology, and I'm going to describe Whitehead's theorem. So Whitehead's theorem concerns homotopy, high homotopy groups. What is high homotopy groups? So if you have a topological space X and a point X and X, you can define the nth homotopy group of X at X as, first of all, as a set of continuous maps from the nth hypercube into your space, so that the boundary of the nth hypercube is mapped to a point. So this is a map of pairs. And you look at the set up to this equivalence relation, which is just a homotopy of maps. And basically, these high homotopy groups, this definition works for n equals 0 as well, but the point is kind of irrelevant. These high homotopy groups tell you about the topology of your space. They're pretty good ways to distinguish spaces. They can tell you about the existence of holes or how twisted your space is, etc. And these high homotopy groups, as the name suggests, come with a group structure. So if you're given two elements of the nth homotopy group at X, these are maps from the nth hypercube into the topological space, so the boundary maps to little x. Then you can define the composition, you can find a group operation by sticking together the two hypercubes. You squash the map F and the map G into half their original length, and you fit them into a single hypercube. And note that the boundary still gets mapped to the point X. And this is how the group operation is defined. And I claim that pi n is a group under this operation. And by convention, the boundary of the 0 hypercube, which is a point, is the empty set. Now note that if n is greater than or equal to 2, there's more than one way to compose maps. So here I compose them hypercubes horizontally, right? I squash them horizontally, but you can also compose it vertically. And for n, you have n group operations, like canonical group operations, in this manner. Now this flexibility, the fact that you have more than one group operation, allows you to prove the following proposition. If n is greater than or equals to 2, then the high homotopy group at X is abelian. That's just an exercise for you to do. This is all classical topology. And if you have a continuous map between spaces, you will get that these high homotopy groups are functors. So you get an induced map from the high homotopy group of X at little x to Y at f of x. And we define a topological weak equivalence to be such a continuous map so that all these induced maps in high homotopy groups are isomorphisms. Right, so topological weak equivalence cannot be distinguished by high homotopy groups. As far as the high homotopy groups are concerned, this map can be an isomorphism. And if Whitehead's theorem states that if you have a continuous map of CW complexes, which are spaces built out of spheres glued along boundaries, loosely speaking, then this map is actually a homotopy equivalence, if and only if it is a topological weak equivalence. And as you can see, the backward direction is the forward direction is pretty easy. If you have a homotopy equivalence, you can prove that all the induced maps in high homotopy groups are isomorphisms. But the converse is pretty tricky. And we'll prove something slightly stronger. We'll prove this statement for a wider class of objects, not just CW complexes, because CW complexes are defined using these things called skeletons. So the gluing procedure is very it's quite nice, but we will we'll prove Whitehead's theorem for a class of topological spaces where you can glue things infinitely many times and in any way you like. So I'll just state the definition of a model category here. So a model category is a category C with 3 classes of morphisms: W, called the weak equivalences; Fib, called the fibrations; and Cof, called the cofibrations. and we'll want it to satisfy 5 properties. And all these properties are categorical nonsense for the moment, but they have important topological implications. So the first property considers the category C, and you want it to be complete and co-complete, which means that you want C to have all limits and co-limits, all small limits and co-limits. So, for example, examples of such categories are category of sets, category of topological spaces, any abelian category, for example, the category of abelian groups, category of groups itself, more abstract categories such as category of functors from C to D when D is complete and co-complete, and certain categories of sheaves, for example, sheaves of sets on a site, if you know about that. And being complete and co-complete basically means you can glue objects, loosely speaking, in any way you like. And the second property is the weak equivalences. Want them to be some form of equivalence. So they satisfy these 2 out of 3 properties. So for all occurrences of this diagram, if you have maps F and G between A, B, and C, if any 2 of G composed F, G, or F lie in W, then so does the third. And furthermore, the class fib and cof are stable under composition, just under composition. Examples of things satisfying 2 out of 3 property include isomorphisms, right, and homotopy equivalences in category of topological spaces. So the third property is quite abstract. You want these class of morphisms fib, cof, and W to be closed under retracts. What I mean by retracts of a morphism. If you're familiar with retract of a topological space, then this is exactly the same thing. It's a retract of an arrow. So whenever you have a diagram like this, note here that if you do R and S, you get 1 on A. If you do T and U, then you get 1 on B. We say F is a retract of G. And so closure under retracts means that if G is one of fib, cof, or W, then so is F. Right? Some trivial example of retracts in category of topological spaces. If you have a retract of pairs, right? So you have a retract of topological space, and each topological space here comes with a subspace. So it has a subspace A, which gets mapped to the subspace X of Y, and it gets mapped to a subspace A of B. And if this is a retract on a subspace as well, then you get a retract of arrows. So for example, here's an example. So if you have this pair on the left, so you have like a donut, like a punctured disk with a ray, and you contract it to S1, and this ray gets contracted to a section, and then you include this S1 back into the punctured disk, and the section gets mapped to the ray. And this is a retract of the arrow which includes the subspace X into Y. Right? So that's a basic example of a retract. But retracts can be much more wild, of course. Fourth property is considers liftings of maps. Now, liftings of maps in topology are ubiquitous, especially in homotopy theory. And this property 4 states that for any square like this, any solid square which commutes, so that either I is a cofibration and a weak equivalence, or P and P is a fibration, or I is a cofibration and P is a fibration and a weak equivalence, then the square can be solved for some H. It doesn't have to be unique. So you can find a lifting of these squares, or a solution. Lifting properties come up in homotopy theory. For example, if you've seen covering spaces, you have a square like this. X tilde here is a covering space of X. And if U is simply connected, and you have a diagram, the solid diagram, if it commutes, right? So you fix the point in U, and this point will determine a unique lifting H of the map below into your covering space. Right? If you're familiar with covering spaces, otherwise don't worry about it. And more generally, if you have class of morphisms A and B in the category of C, we say A satisfies left lifting with respect to B. Equivalently, B satisfies right lifting with respect to A if for any map little a in A and little b in B fitting in a diagram like this, then we can solve it for some H, not necessarily unique. So the A's here on the left, so they satisfy left lifting with respect to B, and B satisfies right lifting with respect to A. Right. I hope you can see my green mouse cursor. Try to make it as visible as possible. Last property. So the properties until now, up until now, the fibrations and the cofibrations can be the empty set. There is no restriction on. There's no connection really between the category C itself and the fibrations and the cofibrations. So the last property states that there should be enough fibrations and cofibrations, and moreover, property 5 states that for any morphism F in C, it can be factored as follows. So it can be factored in two ways. You can factor it as a cofibration and then a fibration and a weak equivalence, or you can factor it as a cofibration and a weak equivalence followed by a fibration. And these factorizations don't have to be unique. They don't even have to be functorial, although some authors require these factorizations to be functorial. Axioms of a model category. Now let's see how these axioms play a part. How you can use these axioms to prove things. So I'll give you a proof of a lemma. This is the only thing I'm going to prove in this talk. That's like of any content, of any serious content. And I'll show you how to use all these axioms. All these axioms will be used in this lemma, except completeness and co-completeness. So suppose we're working in the model category, and suppose you have a map from A to D called I, which satisfies left lifting with respect to the fibrations intersect the weak equivalences. And in fact, I is a cofibration. So this is a converse to property 3. No, property 4. It's a converse to property 4. Property 4 states that the cofibrations satisfy left lifting with respect to fib intersect W. But it turns out the converse is also true. So how do you prove this? First of all, you take your map I, which satisfies left lifting, and you factor it using property 5. Right, so you can factor it as a cofibration and then a fibration and a weak equivalence. Now, remember, cofibrations are stable under composition. So to show that I is a cofibration, we know IC is a cofibration, so we have to show IFW is a cofibration. But I satisfies left lifting by assumption with respect to fib intersect W. So you can fit this factorization into a square like this, and note that I is a cofibration, and IFW is a fibration and a weaker. Sorry. I satisfies left lifting with respect to IFW because IFW is in fib intersect W. So there's a solution H to this diagram. And now we're going to use the retracts property to exhibit I as a retract of IC, and IC is a cofibration, and therefore I is a cofibration. And this proof used all axioms of a model category except completeness and co-completeness. Now to do this retract argument, we had to use this lifting H here, down here. I'm going to take a second to look at the diagram and convince yourself that everything works out. And in fact, proving a few lemmas similar to this one gives a second definition of model categories. So I've written the definition here. In fact, a model category is a category C with 3 classes of morphisms: W, fib, cof. So that again, C is complete and co-complete. W satisfies 2 out of 3, and fib and cof are stable under composition. Now you can replace you can get rid of the retracts property, and you can strengthen property 4, the lifting property, into this following property. The cofibrations are precisely the maps satisfying left lifting with respect to fib intersect W, and cof intersect W are precisely the maps satisfying left lifting with respect to fib. And another lemma would be that you can recover the retract. The retract property is quite useful when you want to prove things, right? So this is a more compact definition of model categories. And of course, property 4 is just the factorizations property as before. Now, a few remarks. You can look up weak factorization systems. You can make the definition be more compact. And the definition is essentially a statement that cof against W intersect fib and cof intersect W against fib are weak factorization systems. Weak factorization systems are just two collections of maps in a category that satisfy these lifting and factorization properties. And sometimes when we have 3 collections of morphisms, W, fib, and cof, which identifies C as a model category, we say this is a model structure on C, right? Because a category can have many model structures, not just one. And it turns out it's a very trivial example of a model category. Well, every model category has to be complete and co-complete. And every complete and co-complete category has a trivial model structure. Now, I got the order of the morphisms wrong here. So I claim that if you have a complete and co-complete category, and you let the weak equivalences be all the isomorphisms, and the fibrations, the cofibrations is everything else, then I claim this is a model structure on C. And I claim that properties 1, 2, and 4 are trivial. So let me tell you why. So property 1 is C is complete and co-complete, but we assume that. Property 2 is W, the isomorphism, satisfy 2 out of 3, which is true. And the fibrations, the cofibrations are stable under composition, but here we took the fibrations and the cofibrations to be overmaps. And 4 is the factorization. I claim that any map can be factored as a cofibration followed by a fibration, which is a weak equivalence. But a cofibration can be taken to be any maps, so you can factor F as F and then the identity on the target. And the identity on the target will be an isomorphism, which is a weak equivalence, and it's also a fibration. And the other factorization is the same. And for the lifting property, you basically have to solve such a square. Say, you have to solve a square like this, where T is an isomorphism. And you can solve it by setting H to be, you do G, and you do T inverse. And I claim this will solve this square. And you also have to solve the square where S is an isomorphism, and this can also be solved. So you can prove easily that this is a model structure. Right. So now you've seen an example of a model structure on any category, which makes sense to have a model structure. And now we're going to do homotopy. I'm going to show you how to do homotopy theory in a model category. And it turns out the homotopy theory for this trivial example is very trivial because it won't really do anything. Like, two objects will be identified if and only if they're isomorphic. So this homotopy theory is kind of boring. So let's talk about homotopy theory in model categories. And I'm going to compare how homotopy theory is set up in a model category and how it works in topological spaces. So let's see how to do homotopy theory in a topological space, in topological spaces. The key object to do homotopy theory in topological space is a cylinder, which is you take an object and you take its product with I. I here is the unit interval, closed unit interval, and you can fit this x cross I into a diagram like this, right? So you have this codiagonal. The codiagonal sends the disjoint union of two copies of x into x in the obvious way, and you can factor this as I0 plus I1, and then the first projection from the cylinder onto X. Now what does this do? Here, the two disjoint copies of X get mapped to the top and the bottom faces of the cylinder in X cross I. And then you project X cross I back onto X, and this is the codiagonal. Right? And why do we care about this? Well, in order to exhibit a homotopy between two maps, F and G, between topological spaces A and B, you want to produce a homotopy, a map H from A cross I, the cylinder of A, into B. And you want it to commute, to make this diagram commute. So basically, if you include A into the top face and apply H, it's your map F. If you include A in the bottom face, or top face in this case, sorry, top face, and apply the homotopy H, then it's the original map G. So H is an interpolation between map F and G, a continuous interpolation. And this is exactly what the commutativity of this diagram is stating. And somehow the fact that this cylinder object for X factors the codiagonal is a key property, which tells us that the cylinder object can be used to do homotopy theory. So how would we do this in model categories? We define a cylinder object for A in a model category C to be a factorization of the codiagonal of A. So any factorization like this, and we require W to be weak equivalence. So we require the cylinder object to be weakly equivalent to the original object. It needs to be related in some way. And here's where it gets interesting. Two maps f and g from A to B are called left homotopic. Left homotopic. If there is a left homotopy H from the cylinder object of A into B, making this diagram commute. And this is in complete analogy to what happens in topological spaces. And I here is just a map that includes the top and bottom, the two disjoint copies of A into the top and bottom of the cylinder object. But there is no top and bottom of the cylinder object necessarily. And we say f and g are left homotopic, and we write tilde L. Now, the fact that you have to choose a cylinder object in the model category to do a homotopy theorem, it's quite bad because there can be some pretty bad cylinder objects. So in practice, we will only work with certain cylinder objects, which we'll call very good cylinders. It turns out that homotopy theory works very nicely when you use these very good cylinders. And if you also restrict to certain objects which are very nice, then the left homotopy, you can get rid of this left. So let me talk about left homotopy. Because in a model category, there's also a notion of right homotopy, which is completely dual to left homotopy. So you can define a path object, which is dual to a cylinder object, as the factorization of the diagonal map. Right? And you want this time V from B to the path object to be a weak equivalence. And two maps f and g from A to B are right homotopic, written tilde R, if there is a right homotopy H from A to the path object of D, making this diagram commute. So it's completely dual, the notion. But we will only talk about left homotopies because we will see that if we restrict our category down, eventually we will have the left and right homotopies coincide. And you can, the path object in topological spaces is just the set of maps from the unit interval into B with a certain topology. But as you can see, it's quite nasty to work with this. It's much nicer to work with a cylinder object. Now, cylinders can be poorly behaved. For example, there's a trivial cylinder. You can take the cylinder of A to be A itself, because I didn't prove it, but all identity maps will be weak equivalences. In fact, the three classes of maps, W, fib, and cof, contains all the identities. It's quite easy to prove. And what does a trivial homotopy look like? What does a homotopy involving the trivial cylinder look like? So suppose f and g are maps from A to B. And suppose there's a homotopy between these two maps involving this trivial cylinder A. And this means that this diagram commutes. But note now that our map I is the codiagonal itself. So, and the codiagonal composed with each of the conclusions of A into the disjoint union of two copies of A is just the identity on A. So this composition and this composition is just the identity on A. And so this states that F equals H equals G. So two maps are homotopic via the trivial cylinder if and only if they're the same, which is kind of boring. So this tells us that we need to work with nicer cylinders. And I will define what I mean by a nice cylinder. So we say a wedge I is a good cylinder. If you look at this map here, this diagram here, we define the cylinder a wedge I. We say it's a good cylinder if I is a covibration, and a good left homotopy is a left homotopy involving a good cylinder. And we say a wedge I is a very good cylinder if also W is a fibration. And a very good left homotopy is a left homotopy making use of a very good cylinder. And why do we care? Why do we want to use very good cylinders? Because as it turns out, if you have a single very good left homotopy, which is F and G, then involving a certain very good cylinder, then you have a very good left homotopy involving any very good cylinder. So you've removed the need to distinguish a very good cylinder when you're working with very good left homotopies. Now let me prove why you can do that. So suppose you have one very good left cylinder here, and you have another very good left cylinder here, a wedge I dash. Right? Then they're both factorizations of the codiagonal, so you can fit them into a square like this, right? And J is a cofibration, and W is a fibration and a weak equivalence. So you can solve this square by lifting, find some H. So somehow both of these factorizations of the codiagonal factor through each other. And so for any left homotopy, as in this diagram, between F and G, which involves the original very good cylinder A wedge I, you can factor this I as J and then H. So if you had an original homotopy big H between F and G, now you have a homotopy H composed little h between F and G, which involves the new cylinder. And you can work backwards. If you have a very good left homotopy using this new cylinder, you also get a very good left homotopy using the old cylinder. Now, here's another lemma. We want to upgrade cylinders to very good cylinders. And the first step is quite easy. So every left homotopy can be upgraded to a good left homotopy. And by upgrade, I mean, if you have a left homotopy involving any cylinder, you can produce from that a good left homotopy involving a good cylinder. So if you look at the top of this first diagram, we have a cylinder A wedge I. Then we can factor I as a cofibration and a vibration weak equivalence. So IC and IFW. And we get a good cylinder on the bottom. It's a good cylinder because composition of W is in W, and this is a cofibration. So this is a good cylinder. Now let's say you have a homotopy between F and G involving just the cylinder. Then you can factor I as IC followed by IFW, which I didn't draw in this diagram, but I wrote down here. And then H composed with IFW is now a homotopy between F and G using the good cylinder. And it's a good left homotopy. Now sadly we cannot upgrade the good left homotopys to very good left homotopys. In order to do that, in order to upgrade to very good left homotopys, so we don't have to worry about the choice of very good cylinder. And what the next step will also do for us is remove the need to distinguish between left and right homotopys. So in order to get these two improvements in our homotopy theory, we need to restrict our category to a full subcategory CCF. And these objects are going to be very nice objects. Okay, so here's a definition. Let T and I denote the terminal and initial object in C. We say an object A is fibrant if the unique map from A to the terminal object is a fibration. And we say A is cofibrant if the dual notion occurs. And the way to remember this is fibrations behave well with respect to limits, and the terminal object is a limit. And cofibrations behave well with respect to colimits, and the initial object is a colimit. And let CCF be the full subcategory of fibrant cofibrant objects, so objects which are both fibrant and cofibrant. Then we have the following two lemmas, which I shall not prove, but they are quite simple to prove. Each is about one side of A4. And there's a lot of diagrams, so the arguments aren't that long. So if A is cofibrant and then B is fibrant, then the left homotopies and the right homotopies in this set hom from A to B, they coincide. And they form an equivalence relation, so we can just refer to them as homotopies. So we remove the need to distinguish between left and right homotopies. And lemma 2 states, if B is fibrant, then every left homotopy in the set homs from A to B can be upgraded to a very good left homotopy, not just a good homotopy, left homotopy. And as a result, when you work in this full subcategory CCF, then we have a nice homotopy theory. Right. And you also have a notion of homotopy equivalence now. So if you have any two objects A and B in CCF, a map F from A to B is called a homotopy equivalence if there is a homotopy inverse G from B to A. So that composing either way gives you the identity. Is homotopy equivalent to the identity. Very important. So it's defined completely analogously to topological spaces. And homotopy equivalence is an equivalence relation on the objects of CCF, completely analogously to topological spaces. And we can define the homotopy category of a model category as to be whose objects are the objects of CCF, but whose morphisms are the morphisms of CCF modulo an equivalence relation on the morphisms. And this equivalence relation is the homotopy equivalence relation. Right. And so we've established a homotopy theory for model categories, and now But the issue is we have to restrict down to this smaller category of nice objects. So you might be thinking, what about a generic object in C? How do we relate this object to CCF? And the claim is that you can do this. We have this notion of fibrant and cofibrant replacement. And the fibrant and cofibrant replacement allows you to replace any object of C with a fibrant cofibrant object in a very nice and uniform manner. So for any object A and C, fibrant replacement is a factorization of the unique map from A to the terminal object using the last axiom of model categories. So you factorize it as a cofibration and a weak equivalence and a fibration, as in this diagram. But now AF is fibrant because this unique map here is a fibration. And I is a weak equivalence. So the object A is a weakly equivalent to this fibrant replacement, which is very nice. And the cofibrant replacement is defined completely dual to this notion. And the thing is, we can do a fibrant replacement and a cofibrant replacement after that to get a fibrant cofibrant replacement. So taking any object A, you do a fibrant replacement like this first, and then you take your fibrant replacement and you do a cofibrant replacement of that. I claim the object ACF here is fibrant cofibrant, and it's weakly equivalent to the object you started with. And I claim that this process is functorial once you quotient out by homotopy equivalence. So this process produces a well-defined functor gamma, I don't know what this is, from your category C into the homotopy category, which takes an object and sends it to its fibrant cofibrant replacement. And maps are defined, the maps are sent via lifting properties. You can see how the maps behave. No, that's regard. And we have this following theorem, the main theorem, the key theorem, which is Whitehead's theorem for model categories. And it states that if you have a model category CW, fib, and cof, and you have the full subcategory CCF of fibrant cofibrant objects, then the class W coincides with the class of homotopy equivalences in this full subcategory. And the proof is not too difficult. It's about two sides of A4, assuming a few lemmas maybe. And it's just Sudoku using all the axioms of model categories. It's very nice proofs. You can look it up in Mark Hovey's book. And the key idea, what we have managed to do here is we've succeeded in inverting the class W. So we constructed this homotopy category C, and in this homotopy category, every weak equivalence is an isomorphism, right? And moreover, any object of C can be approximated by some object inside this homotopy category using this functor above. So we have a well-behaved homotopy theorem as well. And what does this mean for the topological version of Whitehead's theorem? Well, we're gonna want W to be the class of topological weak equivalences, and we want C to be topological spaces. We'll prove that all CW complexes are fibrant cofibrant in a certain model structure, and this will mean that in the subcategory the weak equivalences coincide with homotopy equivalences, and we're gonna have to prove that homotopy equivalences from the model category perspective are exactly homotopy equivalences in classical topology. After that, we will be done. We would have proved the Whitehead's theorem. Right. But before we do that, I just want to give another example of a model category, which is a simple, slightly more non-trivial than the trivial example. So let's see the category of sets equipped with an equivalence relation. And the morphisms are maps between sets which respect this equivalence relation. We can also think of C as the category of partition sets, and the maps are set maps which respect the partitions. And this can be given a model structure where cof is the injective maps, fib is the maps where if you take any class in A and you look at the class it gets sent to in B, then this particular map is onto. And W is the maps which induce a bijection on the quotient by the equivalence relation, right? So you can all the maps in C will induce maps on the quotients because they respect the equivalence relation. And I claim that the homotopy theory you get by considering this model structure is a homotopy theory of relations. Namely, that the functor we constructed before, which sends an object of C to the homotopy category, will just send a set A to the set A modulo its equivalence. And maps between sets will just get sent to maps between the quotients by the equivalence relations. Right? In particular, every object of C is fibrant cofibrant, because in set, the initial object is the empty set, right? The terminal object is the point. So the unique map from the empty set into any set is injective. Right? So every set, every element of C is cofibrant. The unique map from any set into a point is going to be onto restricted to any class. Easy to check. And so every object of C is also fibrant. And note in particular that the homotopy category of C is equivalent to the category of sets, because any set is realized as a quotient of itself, for example, by the trivial, by the weakest equivalence relation you can put on the set. So there's an example it's quite easy to prove this particular example. So now we're going to talk about the main content of the talk. So we work with topological spaces, and we let W be, as we said, the topological weak equivalences. So the continuous maps which produce isomorphisms in all higher homotopy groups. And we want to put a model structure on this category where W is the weak equivalences. And so we have two sets here. We have the set I of boundary inclusions of the sphere onto the disk. And our convention here is that the S0 is just 2 points, the boundary of the, and S minus 1 is just the empty set, the boundary of a point, as we said earlier. J is the set of inclusions of the n disk into the first component of dn cross I, where here x is going to get sent to x, 0. And these two sets somehow control the homotopy theory of classical homotopy theory. And how do these two sets give us a model structure? Now, I don't have time to talk about this, but there is a way to construct model structures called cofibrantly generated model structures. So the model structure we're about to define now is going to be cofibrantly generated. And what does that mean? It means you start with two sets, I and J, and you reflect them a few times. And eventually you will get your cofibrations and your fibrations, and you have to prove that there are fibrations and cofibrations. But the theory of cofibrantly generated model structures makes life a bit easier, because in general it's very difficult to prove something as a model structure. So we define for any category C and any class of morphisms I, the I injectives are the maps satisfying right lifting with respect to I projectives are the maps satisfying left lifting with respect to I. And you reflect once more. So the I cofibrations are the maps satisfying left lifting with respect to the I injectives, and the I fibrations are the maps satisfying right lifting with respect to the I projectives. And we claim simply by reflecting the class of morphisms I twice, like this, you will get your fibrations and cofibrations. And so in our particular example, we let the fibrations be the J injectives, where J is this set here, and we let the cofibrations be the I cofibrations, where I is this set here. This is what generally tends to happen in a cofibrantly generated model structure. And we claim that this is a model structure on topological spaces called the Quillen model structure. And it's quite long to prove this statement, but it's basically it's a long proof made up of many simple steps. Well, not so simple, but you can go read Markovi's book and they do it there. Now, I haven't talked about cell complexes at all until this point, so how do cell complexes play into this? So we're going to have to construct a general cell complex in a category. So let lambda be an ordinal and say a category. A lambda sequence is a colimit preserving functor from the ordinal into a category. And here ordinals, we treat ordinals as categories because every ordinal is a total order. So if you take supremums in your ordinal and you map that over to C, that's just going to be the colimit of the sequence of maps And why am I talking about ordinals? Because we want to talk about composition of infinitely many maps, right? So you can't compose infinitely many maps. What's the next best thing you can do is you can take the co-limit of infinitely many maps in succession. So this is exactly what we do. So we have an ordinal, which describes a set of maps we want to compose, and we define the transfinite composition of a lambda sequence to be the map from 0 to the co-limit of this sequence. Right? If you treat the lambda as a diagram, so it's just the co-limit of this diagram, I guess. The map from S0 into the co-limit of this diagram. And now we can define a relative isel complexes. So if I is a class of morphisms, then we say a map is a relative isel complex if there's an ordinal lambda and a lambda sequence S, so that F is a transfinite composition of S, and for any beta, so beta plus 1 is less than lambda, we have this square. We have a square like this, which is a push-out square. So the consecutive maps showing up in the diagram are going to be push-outs by maps GB in I. Once again, saying F is a relative isel complex is just saying F is a transfinite composition of push-outs along I. Right? And in our case, I was the set of boundary inclusions. Right? So saying something is a relative isel complex in the character topological spaces just means saying F is a relative isel complex, say. It just means you can attain the space B from A by gluing A along disks, gluing disks to A along their boundaries transfinitely many times. And you can see where this is going. We can now define isel complexes. So an object A of C is an isel complex if the unique map from the initial object to A is a relative isel complex. So if you can build A by gluing together transfinitely many times along maps in I. So in particular, note that any CW complex will be an isel complex, where I is this class of maps here, and a priori this the isel complex is larger than this class of CW complexes because we don't care about skeletons. You can glue these disks in any way you want. Right? And the lemma states that the isel complexes are contained in the I cofibrations for any class I of morphisms in any model category, I guess, or in any category where this makes sense. And the way you prove this is, it's easy to see that I is an I-cof by definition, and you can prove each of these statements. The I cofibrations are closed on the push-out, and more generally, the cofibrations in any model category will be closed on the push-out. And the I cofibrations are closed under transfinite composition. This is slightly trickier, but you can still do it by transfinite induction, for example. And putting all these three together is sufficient to prove the lemma. Right, so all CW complexes are I cofibrations. Now remember, the I cofibrations were defined to be the cofibrations. Right? And I claim that I'll tell you later why all topological spaces are fibrant. But CW complexes here, we just showed they're isel complexes, and we just showed by this lemma that isel complexes are cofibrant. Right, because all relative isel complexes are cofibrations. So why are all topological spaces fibrant? Because being fibrant just means the unique map from your space into the point, from your space X to the point, is a J injective. Right? So you take any map in J. Remember, the maps in J were inclusions from Dn into Dn cross I, where X is sent to X, 0. And you want to solve this any such square. But it's very easy to solve such a square. If the map on the top is F, you just set H to be send X at time t to F of X. So it's the constant map. So H is the extension of F to all time constantly. And this will be a solution of this diagram, and it always works. So in particular, all CW complexes are fibrant cofibrant, which was one of the things we needed to prove. And so to prove Whitehead's theorem, it will be sufficient to prove the following two lemmas. So it will be sufficient to prove that the standard cylinder object for any topological space A, which is just the product of A with the unit interval, we have to prove that it's a very good cylinder when A is a CW complex. Sadly, this is not true in general. So the first lemma states that the standard cylinder object is a cylinder object, and pi1 is a fibration. Well, pi1 is just it's actually deformation retract, so it's going to be a homotopy equivalence, and so it's going to be a weak equivalence. And why is pi1 a fibration? It suffices to, again, solve this square here for all maps in J. And I've written down here how you can solve this square. You can work it on yourself. You can work out how to solve the square yourself. But it's quite simple. So pi1 is a fibration and a weak equivalence for all topological spaces A. But generally, the standard cylinder object in general is not a very good cylinder object. So this map I0 plus I1 is not always a cofibration. So we need to use the next lemma, which is if X is a ISL complex, then the map I0 plus I1 is a cofibration, and the standard cylinder object is a very good cylinder. And the idea is to use transfinite induction, because note you might prove this in topology. If you have a product of finite CW complexes, it's again a finite CW complex. You use this sort of prism construction. And the same idea applies here. If you have here I wrote A for X, which is a mistake. But let's say if you have a ISL complex, the map I0 plus I1 is the inclusion of the top and bottom of the cylinders, of the standard cylinder, right? And you want to fill out the gap in between by gluing together disks along the boundaries. And this can be done when A is an ISL complex. You have to do it transfinitely many times. And it's again, looks a bit like the prism construction. And I omitted the details because it's kind of an ugly proof to formalize. But we get that the standard cylinder object attached to any CW complex is a very good cylinder, and therefore by all the theory built up, Whitehead's theorem will follow. That weak equivalences between CW complexes will produce homotopy equivalences. And here are some remarks. In the Quillen model structure, the fibrations are called Basset fibrations, right? So the Quillen model structure generalizes classical homotopy theory. The cofibrations are exactly the maps which are retracts of relative ISL complexes. And now retracts here are retracts of arrows. And by the CW approximation theorem, which states that every topological space is weakly equivalent to some CW complex. And this essentially is essentially stating, giving you the cofibrant replacement of any topological space. Right. So the CW approximation theorem tells you more about the functor gamma or whatever this is from topological spaces to the homotopy category topological spaces, because it's start with any topological space. It's weakly equivalent to a CW complex, which is fibrant cofibrant. And so it will send any topological space to a weakly equivalent class of CW complexes, right? Because weak equivalence in the homotopy category is just a homotopy equivalence, right? So somehow CW complexes there is enough of them in there are enough of them in top, and they play a key role in the homotopy theory. Right, so that's the main content of my talk, but I just wanted to talk quickly about a few more examples of model categories. So, in particular, the third one is very interesting. So, the category of sets has precisely 9 model structures. So, you can go to this site here, and this guy basically constructs the 9 model category structures on sets, and you can read through it. It's not too difficult. And the maps, the model structures are kind of boring sometimes. As you can see, the cofibrations, the fibrations tend to be like maps like bijections, surjections, injections, some wilder maps here. And you get different kinds of homotopy categories as well. Okay. A second example is a a nice example. I'll be quite quick with it. So if R is any Frobenius ring, left Frobenius ring, so this means injective and projective left modules are the same. And let's see the category of left modules, then you can give C a model structure. Again, it's cofibrantly generated, so you start with sets I. I is just a set of left ideal inclusions into R. J is the zero ideal inclusion, and W is the set of stable equivalences. And a stable equivalent, two maps F and G between left R modules are stably equivalent if you can factor their difference through a left projective R module. And the notion of stable equivalence is built in the same way as a homotopy equivalence is built out of a homotopy between maps. So F from X to Y is a stable equivalence if there's a map G from I to X, so that the composition F and G and F are stably equivalent to the identity. And you set the fibrations to be the J injectives and the cofibrations to be the I cofibrations. And I claim the category C with these three classes of morphisms as a model category. And the homotopy category is going to be called the stable category of left R modules. And it's a nice example because all objects of C are fibrant cofibrant. And yeah, it's just a nice example. Like examples of rings which are Frobenius include any group algebras over a finite group, I guess, and many Hopf algebras. And so the second example can be of importance to people interested in representation theory or groups more generally. And I'll come to our most interesting example. So if R is a commutative ring and you look at the category of chain complexes bounded below, so vanishing in negative degree basically, and I can give the chain complexes a model structure. So W is the quasi-isomorphisms between two chain complexes. Quasi-isomorphism between chain complexes is just a map of chain complexes which induces isomorphisms in cohomology. And the fibrations are going to be degree-wise epimorphisms between chain complexes. Now, in the category of chain complexes, degree-wise epimorphisms are the same as epimorphisms, and the monomorphisms are also the degree-wise monomorphisms. But saying degree-wise epimorphisms is more explicit because you know what they look like. And the cofibrations are the degree-wise monomorphisms with projective cokernel, degree-wise projective cokernel. I claim this forms a model structure on the chain complexes called the projective model structure. And all objects are fibrant because the unique map from a chain complex to zero is always a degree-wise epimorphism. And now we ask ourselves which objects are cofibrant. So for an object A to be cofibrant, we want the unique map from zero to chain complex A to be a cofibration. So we want it to be, well, it's always a degree-wise monomorphism, but we also want degree-wise, we want it to have projective cokernel. But the cokernel of the map from zero is just the objects of A. So this map is a cofibration if and only if A consists of projective R modules. So the cofibrant objects in this model category are going to be chain complexes made up of projective modules, projective R modules. And cofibrant replacement of a chain complex A, remember, it's just a factorization of the unique map from zero to the chain complex, as follows, where H is a cofibration and F is a fibration and with equivalence. Then P is a fibrant cofibrant, so it's a projective. It turns out that cofibrant replacements in this model category are just projective resolutions of chain complexes because P is made up of projective modules and F is a quasi-isomorphism, which is degree-wise epimorphic onto A. And in fact, you can prove, this is a very nice fact, that the homotopy category of the chain complexes bounded below is the bounded below derived category of R modules. So, so if you're familiar with the construction of derived categories, you'll see that there's many steps involved. You have to pass two triangulated categories. You have to quotient, but first you have to quotient by homotopy, chain homotopies, and you have to do calculus of fractions. But here we managed to invert quasi-isomorphisms in a single step. And in fact, one way to look at model categories, it's a very powerful way to invert a class of maps W. It's much more powerful than calculus of fractions, for example. And yes, we've done it in a single step. And in fact, homological algebra is just a special case of homotopy theory. And so that's just my note here. And you can do the same thing with, you can define an injective model structure in the same way, and you can also define a model structure on unbounded chain complexes. Yeah. And here's some remarks. So yeah, you can do the injective model structure as well. And I haven't talked about this, but there's a notion of morphisms between model categories, so they preserve structure. And these are called Quillen adjunctions. They have to be adjunctions. And for example, Fried, it's even nicer because the notion of Quillen adjunction generalizes the notion of left and right derived functors. So the left and right derived functors are going to be Quillen adjunctions. And I haven't studied this in much detail, but it's very nice, and it provides a stronger viewpoint to derived categories. And the reference for all of this is Mark Hovey again, model categories, and chapters 1 and 2, basically. Chapter 2 is all of the examples in detail. Chapter 1 is general theory. And again, most of the work goes into proving that a category has a model structure. Once you have the model structure, it's quite easy to prove great things. So that's my talk. Thank you very much for listening.